Hello students, in this session we are going to analyze about the magnetism in matter. We know there are different type of materials. Certain materials will not exhibit any magnetic properties. Okay, certain materials will be natural magnets. Certain materials can be made into magnets. Okay, different types of materials are there. So we are going to see what is the reason for magnetism in material. Okay, so the primary reason for magnetism is, okay, the reason for magnetism in a matter, in a material, or in a thing is the magnetic dipole moment present in atoms. If atoms join together will become the matter. If atoms exhibit magnetic properties, then that solid or that matter will exhibit magnetic property. So if an atom has magnetic moment, definitely it will have magnetic property. Okay, example, suppose if an electron is rotating around the nucleus, and if a electron will be spinning by its own, nucleus also spinning, all these will contribute magnetic moment. Okay, so now we will see. Suppose if an electron is moving like this, electron is moving in this direction, obviously current will be moving in this direction. So if I consider a clockwise, okay, so looking from here, in whichever way you want, you can take. Suppose if electron is moving like this, then current will be like this. There will be magnetic moment in this direction. If current is in this direction, okay, say for example like this, okay, if the current is in this direction, I am considering like this, then this is going to be the direction of what? Magnetic moment. So this is current I. So electron will be moving in that direction, current will be moving in this direction. Okay, this will exhibit magnetic moment. The problem is certain material will have two paired electrons and they will have opposite magnetic moment. The direction of each electron will be opposite. The direction of magnetic moment due to each electron could be opposite. So magnetic moment will be cancel each other. Net magnetic moment will be zero. Okay, so say for example, suppose if this is an orbital, this is going to be the magnetic, this is one electron, this is another electron, I mean the magnetic moment due to electron, one is this direction, another is this direction. So in this case the net magnetic moment will be zero. Okay, if there are two electrons and that paired electrons are contributing magnetic moment in the opposite direction, they will cancel each other. Okay, so these kind of materials are called diamagnetic materials. Okay, now suppose if there is only, okay, one electron in an orbital, and if this is contributing magnetic moment, so there will be a net magnetic moment for this one. So this will exhibit magnetic properties. So this is the real reason for magnetism in materials. Okay, pause the screen and please note it down. Suppose if we take a material, its magnetism is due to the dipole moment from atoms. So we can say dipole moment is due to number 1, rotation of electrons. So this is what we have just seen now. Due to rotation of electrons, there will be magnetic moment. Another thing which contributes is like not rotation but spinning of electrons. Or spin of electron, this is enough. Spin of electron. Third one, due to spin of nucleus. That is, electron can rotate like this. This will contribute current. This will contribute magnetic moment. That is what is this. Other than that, that electron will be spinning. Then nucleus also will be spinning. Okay, this will contribute very less. Okay, so negligible amount. We don't consider this. Negligible. The contribution of magnetic moment due to this is negligible. This is what is major. Okay, so we consider the rotation of electrons only in analyzing the magnetism in matter. Okay, so this is one point. Please note it down. Okay, suppose if you take a specimen material, suppose if this material contains atoms with magnetic moment. I have said M net is equal to 0, that is also mentioned here, not that type. Here there will be some magnetic moments. So what will happen based on the orientation of atoms? Here this magnetic moment will be in different directions. This is how it is going to be. Okay, if we take a specimen or a small piece of material, if we take, okay, then this is how it is going to be. Now suppose through some process, if we can make it into this form, if we can make it in this form, then what is this? This will exhibit magnetism. Okay, suppose if current is in this direction, I am curling the fingers like that. If the current is in this direction, magnetic field will be in this direction and magnetic moment also will be in this direction. Correct or what? So this will exhibit what? Magnetic field, magnetism in this direction. Just like this is south and that is north. This will exhibit magnetism. So what is the process of converting this into this? So the question is like how can I orient this magnetic dipoles in a particular direction so that this will exhibit magnetic behavior? So two methods are there. One is by lowering temperature. Okay, if we increase the temperature, this orientation will be lost. That is why we say at a very high temperature magnetic properties will not be present. So by lowering the temperature we can get back the magnetic properties. Another thing is by applying external magnetic field. By applying external magnetic field. So if we can apply an external magnetic field like this, okay, then this kind of random magnetic dipoles will align in this direction. Okay, so why is it so? Why this will happen? What is the I will explain this a little bit. This is just like so suppose if this is a magnetic dipole, suppose if there is magnetic field in this direction, then we know here this will experience what? A force. This will experience a force, and in this here this will experience another force in the opposite direction. So there will be presence of torque, and when torque is there, it will rotate and it will come to stable equilibrium. Okay, so then what will happen? This will come to stable equilibrium. Okay, this will come to stable equilibrium. Okay, clear. That is the reason by applying external magnetic field, this will come to in the proper orientation, and there will be magnetism. Clear? Okay, please note it down. So I said if there is a pair of electrons with opposite magnetic moments, okay, here net magnetic moment will be 0, so there will be no magnetism. These kind of materials are called diamagnetic materials. Suppose if there is only one electron, or if the electrons are not paired, if it is rotating in one direction, there will be current and there will be magnetic moment, and this will exhibit magnetism. So those materials which exhibit magnetism are called, we can say, paramagnetic material and ferromagnetic material. Okay, so they will exhibit magnetism. We will get into the details of that, okay, later. Now you can understand that this doesn't have any magnetism, this has got magnetism. Clear? Okay, so when we apply an external electric field, this will get magnetized. Now we will study about magnetizing. If we keep a material, we can magnetize it. We can make it into a magnet by applying external field. Okay, so next topic is magnetization vector. This is a measure of how much a material has magnetized. Okay, by applying external field, okay, we can make a material, we can magnetize a material. Okay, the magnetic properties can be given to a material. Okay, so that measure is what is magnetization vector. The simple definition is magnetization vector is the magnetic dipole moment per unit volume. Magnetic dipole moment per unit volume. Okay, so how much magnetic dipole moment is there, that much it will be magnetized. So magnetization vector, this is equal to the magnetic moment per unit volume. So this is a vector. Magnetic moment is also vector. Magnetization vector is a vector. Sometimes this I will be used as M also. So if I use M, then that will be confusing, since this magnetic moment we are using M. Pole strength already we have used a small m. So again, so that is the reason I am using I here. So magnetization vector I is equal to magnetic moment per unit volume. How much it has been magnetized, that is the meaning. So its unit is what? Ampere, NIA, right? NIA. So ampere meter square, and divide by, this is nothing but meter cube. Okay, so finally ampere meter raised to minus 1. Ampere meter raised to minus 1. Okay, so this is the unit of magnetization. Okay, suppose if we take specimen. Okay, so this will be, certain will be in order. So if it is not completely magnetized, some will be in order, but all the dipoles may not be in order. So how much it is magnetized, that is what is magnetization vector. Please note it down. Clear? Now how this is done? Okay, this is done by applying magnetic field. Suppose if a specimen, if we take this specimen, can be in different order. This is randomly, magnetic moment will be like this. So now suppose what happens, if we apply a magnetic field, a powerful magnetic field along this, what will happen? They will come in order. They will come in order. Okay, so how much we apply, that much magnetized it will become. If we apply a reasonable magnetic field, some magnetization will happen. If we apply strong magnetic field, it will become strongly magnetized. That is what. Clear? Okay. Okay, now we can write this as south north, south north, south north, south north, south north, south north, south north. Just like this it is arranged. Right, now what will happen? What will happen if this is external magnetic field? If this is external magnetic field, now what happens is when this is magnetized, what will happen? There will be, since this is aligned, there will be, when this is magnetized, there will be magnetic field due to this also. So this is internal magnetic field. There will be internal magnetic field also. When external is given, dipoles will be aligned, and there will be internal magnetic field also. Okay, so magnetization vector is nothing but the magnetic moment per unit volume. Okay. Next is magnetic intensity. Magnetic intensity or magnetizing field intensity. Okay, magnetic intensity or magnetizing field intensity, it is denoted as H. This H is not magnetic field. When we say magnetic intensity, magnetic field intensity, need not think like this is B. Its unit is different. I shall tell the unit now itself, so that its unit is ampere meter raised to minus 1. Same as what? Same as the unit of I. Okay, now we will discuss this. Now suppose the net magnetic field, if we consider, suppose if we keep a specimen here, I applied external magnetic field, so randomly oriented dipoles is now aligned in a particular direction, in the direction of field. Now due to this internal magnetic field also developed. Correct. Now I could say that net magnetic field is nothing but the magnetic field due to external magnetic field and due to internal magnetic field. So net magnetic field is equal to what? Actually, now external magnetic field is also there and internal magnetic field is also there. Net magnetic field is clear or what? So we can say that, okay, this B net depends on number 1 external factor, number 2 internal factor. It depends on external factor as well as internal factor. Okay, so this external factor is what? External factor is the applied magnetic field. Maybe the magnetic field, suppose if we keep a solenoid, okay, if I am applying current, okay, so current is moving in this direction. So if the current is moving in this direction, okay, current is moving in this direction, then there will be magnetic field is in this direction. Suppose if I keep a material there, a soft iron core, if I keep a soft iron core here, due to this solenoid, this external magnetic field is there. Now because of this external magnetic field, what will happen? Here the dipoles will be aligned and there will be internal magnetic field also. So that is what is this one, and external magnetic field is due to this solenoid. Clear or what? Note it down. Clear? Okay. Now this internal factor, can I write it as internal factor is I? Internal factor is I. Okay, internal factor is I. Internal factor can be said as I. The external factor is what is H, magnetic intensity or magnetizing field intensity. So I could say that, okay, both of them are together contributing the net magnetic field. So I could say B net is directly proportional to the internal factor plus the external factor. Internal factor plus the external factor. So when we remove this proportionality, we can write this is nothing but mu naught into I plus H. Mu naught into I plus H, where mu naught is the permeability. Okay, so please note it down. Okay, next students, magnetic susceptibility. Okay, what is this? Okay, see, magnetization vector, that is I happens due to whom? Due to external factor, that is due to H. So magnetization happens due to magnetizing field intensity, correct or what? So I could say that this magnetization I is proportional to what? H. I depends on H, correct or what? So if we increase the external magnetic field, that much magnetization will happen. So external magnetic field, see, net magnetic field is what? Mu naught into H plus I. So this mu B net is equal to what? B internal plus B external. I could write like B net is equal to B internal is what actually? Mu naught into I. Magnetization, how much magnetization has happened into mu naught is what is? B internal plus mu naught into H. This is what is the external magnetic field. So how much more the magnetizing field intensity, that much more will be the what? External magnetic field and net magnetic field. So I could say that this I, if we remove this proportionality limit, this is nothing but susceptibility into H. So important relation, you can remember this. Susceptibility is the connecting factor between the magnetization and magnetic field intensity. Okay, I is equal to, this is generally we say zeta. So I is equal to zeta H. Clear? Note it down. Okay, now mu naught, mu m, mu r. Okay, so this is called absolute permeability. Absolute permeability. This is magnetic, or we can say the permeability of a material, we can say permeability of a material. And this is relative permeability. Okay, now this explanation, suppose if we consider a solenoid, current I, if we keep a soft iron core inside, there will be external magnetic field also. There will be external magnetic field here. Okay, due to the current flow, there will be external magnetic field. If we consider external magnetic field, now when this external magnetic field is given, there will be internal magnetic field also. So this is what we have written, like B net is equal to what? B net is equal to mu naught into what? I plus H. Okay, or B net is equal to what? Mu naught I plus mu naught H, or we can write B net is equal to, this is magnetic field due to internal factor and this is magnetic field due to external factor. This is magnetization vector, this is magnetic field intensity or magnetizing field. Okay, now suppose if I consider a solenoid, now I did not keep anything here, this is simply what? Vacuum. Still I am applying external magnetic field. Still I am applying external magnetic field means if I pass a current here, obviously external magnetic field will be developed there. So in this case here I could say that B net is equal to what? B external alone. In that case I could write B external is what? Just remove B internal. I could say this is nothing but mu naught into what? H. So this is what is external magnetic field or net magnetic field if nothing is kept here. Okay, please note it down. Clear? Now since this external magnetic field, I am writing this as B naught, just for our understanding that this is not on any material, this is just happening in air. Okay, this is just happening in air. So from this we can write that mu naught is equal to what? B naught divided by H. B naught divided by H. The magnetic field per magnetizing intensity. Magnetic field per magnetizing field intensity. This is just like how much magnetic field is permeable. I mean, this is what? Permeability. How much came out when we supplied this much what? Magnetizing field. When we supplied this much magnetizing field, how much magnetic field came out? Okay, when it is in vacuum. That is what is absolute permeability. Okay, the meaning of absolute permeability is For an application of H, how much B naught came? This is what is absolute permeability. Clear? Note it down, please. Okay, so B naught is equal to mu naught into H. Okay, now suppose if I take a solenoid, if I considered a solenoid and I supplied current here and I kept a iron core there. So now here external magnetic field is there, and due to external magnetic field, due to the supply of external magnetic field, what also came? Internal magnetic field developed. Okay, so here we could say this net magnetic field is what? Mu naught into what? I plus H. Okay, now what is this I? I is equal to zeta H. I is proportional to H. I is how much is the external magnetizing field intensity, that much will be the magnetization happens. I is equal to zeta H. So can I write this is equal to mu naught into, instead of I am writing zeta H plus H here. So this is equal to what? Mu naught, and H if I take outside, this is nothing but zeta plus 1 into what? H. So now magnetic field B net is equal to what? Mu naught into zeta plus 1 into H. So that is one expression for net magnetic field. So net magnetic field is equal to mu naught into 1 plus zeta into H. Okay, so mark this. This will be useful. Okay. Okay. Now previously we wrote this is when we keep air or vacuum, we write B naught and mu naught. Now this is nothing but we keep a material. This is not what? Air or vacuum. So in this case we can write B net is equal to what? B net is equal to, just like writing this, we can write this as mu m into H also. Mu m into H, just like we have written for this one, we can write this as the permeability of the material, that is permeability of this material into H. External factor also came here, and this material also will come here. Just by comparing this B naught, if nothing is there, if it is just in air, this is mu naught into H. If something is kept, who will take care of that? This mu m will take care of that. Okay, is it clear? So I could say that B net is equal to mu m into H. So note down this also. B net is equal to mu m into H. Now can I compare these two formulae, this and this one? I can compare these two. So note it down. I will erase. Okay, shall I erase this? So by comparing, I can write now mu m is equal to what? Mu naught into 1 plus zeta. Mu naught into 1 plus zeta. Clear? Mu naught into 1 plus zeta. Now mu m by mu naught, okay, that is the permeability of the material with respect to air. Okay, so this is what is relative permeability. So relative permeability, we are getting 1 plus zeta. Important. Okay, so relative permeability is equal to the permeability of the material with respect to comparing to air. Okay, this is equal to, we are getting as, when it comes here, 1 plus zeta. So relative permeability is equal to 1 plus zeta. So B net is equal to mu naught into mu r into h, or mu m into h. Okay, in all these terms we can write. Note it down. So okay students, so this is about the magnetizing field intensity, susceptibility, relative permeability, magnetic permeability, and absolute permeability. Okay, some descriptions on all these relations. Based on all these relations, problems will be there. Okay.